Previously on Pwime Numbewednesdays.
What are Mersenne numbers? These are numbers which are one less than a power of 2. Sometimes they're prime, and those are called Mersenne primes. Sometimes they're composite. Our quest is to find out whether or not there are infinitely many Mersenne primes. Humanity has no idea. We do know that there are infinitely many prime numbers, but as for Mersenne prime numbers, we think there probably are, but we don't know for sure. We've been looking at all prime factors and which Mersenne numbers they divide. Now, the Mersenne numbers that we're going to look at, the composite ones, are going to be the ones with even exponents. How can we visually represent factors? Just subtracting 1 from the corner, we have 2 to the power of n minus 1 represented visually. And perhaps we will meet our destination. Can we do better? Can we show that there is a factor of 3 in our rectangle representation? Can we show that there's a factor of 5 in our rectangle representation? Rectangles! We've built this rectangle. What is this rectangle?
And now the continuation.
Today we're looking more at rectangles. Last week we discovered that when n is even, 2 to the power of n is a square. Who knew? We can take 1 out of the corner, and then we will have 2 to the power of n minus 1. We can build a rectangle showing 2 to the power of n minus 1 by cutting this portion right here and pasting it at the bottom, and we get this. Here it is. Here's the Mersenne number, 2 to the power of n minus 1, as a rectangle when n is even. Now, as a side note, I found this to be very amusing. Algebra. This is from high school. We have a difference of squares. I never even noticed that 2 to the power of n minus 1 is a difference of squares. I guess it only is if n is even, but even still, this was a chuckle moment. We have a square number minus a square number, and so to factor it, what we can do is the square root of this, put it here, and the square root of this, put it here, add a plus and a minus, done. And as I said to myself when I noticed, the proof was in the diagram, but thanks anyway, high school. Now that we have a way to show a factorization of Mersenne numbers when n is even, how can we explore this more?
Hang on, I thought we were trying to explore Mersenne primes. Mersenne numbers that are prime. Why are we exploring Mersenne numbers that are composite and making rectangles out of them and exploring their factors?
Thank you for asking, Self. Here is an answer in the form of a data chart. So, here are all of our Mersenne numbers, 1 less than a power of 2, and here are all of the natural numbers that go in the exponent spot that result in these Mersenne numbers. We are trying to visually see with rectangles the factorizations of some Mersenne numbers. We've noticed that when we have a Mersenne candidate with a prime exponent, but the Mersenne number didn't turn out to be prime, its factors seem to relate back to the exponent somehow. So, for example, 23 relates back to 11 because it is 1 more than a multiple of 11. 89 is also 1 more than a multiple of 11. When this happens again, where n was prime, but the Mersenne number, surprisingly, is not prime, the factors have that same relationship. 47 is 1 more than a multiple of 23, and incredibly, 178,481 is 1 more than a multiple of 23. We haven't proven that this always happens, but it does seem to be the key to finding out
what causes Mersenne candidates to not be prime? We don't have a clear explanation yet for why this seems to happen and when. For example, if we didn't know already that 2 to the power of 7 minus 1, if we didn't know that this is prime, we might think, a multiple of 7 plus 1, that's a prime number. 28 is a multiple of 7 plus 1, 29, that's a prime number. Maybe 29 divides this. Maybe it's the same kind of situation where it has a prime factor that is one more than a multiple of this. But nope, this one's fine, this one is prime. So why is this one prime and this one is not prime? Right now, in a nutshell, we are looking at rectangles to be able to see the prime factorizations of these things that we already know. So we're not quite looking at these ones right now, we're just looking at the ones that we know. We have proven that every prime number, Every odd prime number, will always divide the Mersenne number where the exponent is one less than itself. So 3 divides the Mersenne number where the exponent is 2. 5 divides the Mersenne number where the exponent was 4. 11 divides the Mersenne number where the exponent was 10. 23 divides the Mersenne number where the exponent was 22. We want to be able to visually see what is happening here. And can we see some kind of prediction for when a prime number will also divide a different Mersenne number where perhaps the exponent was prime? So let's look some more at these rectangles and look at some specific examples. We looked at this type of representation last week where we tried just putting 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus that representation in a spiral, and we got that square with the corner missing. Let's try taking this chunk and pasting it on the bottom and just seeing what that looks like. And we can do that with any of the others. Here's one where we've taken this chunk and we just paste it on the bottom. Here's the very first one where we take this little bit and we paste it on the bottom. Now when we show it this way, we realize, the fact that M2 is 1 plus 2 is very nicely shown this way. This gives me an idea. We're only looking at the Mersenne numbers right now where the exponent is even, right? So we're going to have an even number of terms that we can add up, and we're just adding powers of 2. So for this one, what if we group them so that we have 1 plus 2 at the top and then 4 plus 8 at the bottom? Then we get this. It's still the same rectangle, but now we're expressing the 1 plus 2 up here, and we're expressing the 4 plus 8 down here. We can do that with every Mersenne number where the exponent is even. Here it is with the exponent being the number 6. Here's 1 plus 2 plus 4 plus 8 plus 16 plus 32. I love how elegant this representation is. And we know it will always work because we can split the binary representation into 2 groups just like this. Here are the smaller numbers, 1 plus 2 plus 4 up here. And then here are the larger numbers, which are just 1 plus 2 plus 4 times 2 times 2 times 2. And here they are. We know that they will always line up because of this. Here's 1 plus 2 plus 4. And this chunk is this line times 2 times 2 times 2. What else can we see with this layout? Can it show this? This was the whole reason to look at rectangles and how we can show things as rectangles, so that we can tell what is happening with this. for every odd prime p?
Let's see. We know that the prime factor 3 divides m2. Yep, there it is. We can see it as a side length. The prime factor 5 divides m4, and there it is as a side length. We can see it. The prime factor 7 divides m6, and here it is as a factor. I think we have it. I think we have a way of showing our odd prime factors as side lengths.
Yes! Rectangles are working! It shows this one too, right?
No, it doesn't. 2 to the power of 10 minus 1 is going to be our m10. The side lengths of that rectangle representation are going to be 2 to the power of 5 plus 1, that's 32 plus 1, so 33 by 31. And now that I think about it, the bigger this number gets, the closer to a square this rectangle is going to appear. So no, we're never going to see one of those special odd prime number factors in one of these rectangle representations again, at least not as a side length. But we do know, okay, 11 does divide 2 to the power of 10 minus 1. We know that for a fact. 11 divides 33. So in a way, that factor is represented in this side length.
To be continued. Tune in next week to see where our particular prime factors show up in our rectangles. And on Monday, I will play an actual cello song for you right over here by this fireplace. Whichever one you choose, I'll see you next time.
11 is a factor in here somehow.